In section 5.5, we talk about negative exponents and scientific notation. I guess some of you are saying, oh my God, we got negative exponents? I mean, really? Yeah, well, we do, and there's a purpose for them. Generally, negative exponents are used to represent something that's very small, but let me show you where it comes from. The concept of a negative exponent comes from. Now that you know the quotient rule states that if you have a quotient in the form of, say, a fraction, or even if it's not in the form of a fraction, if it's a quotient and two terms have the same base, and you want to simplify the expression, then as long as those two terms have the same base and you're dividing, then you subtract their exponents. So given this example here where it says using the quotient rule, if you have x to the second divided by x to the fifth, ultimately what you get is x to the what? Using the quotient rule, you subtract, so you get x to the 2 minus 5. And that gives you x to the negative 3. Okay? Now, look at it this way. Using the definition of x to some power, what does x squared mean? It means x times x, right? It means x times x, and x to the fifth means x times x. Oh man, I put 5. It means x times x times x times x times x. And if you look at this and you cancel the two x's at the top with 2 of the x's at the bottom, remember these all become 1s. When two numbers cancel through division, when they divide out like that, you're left with a 1 in the top. Remember, it's 1 times 1. That's a 1 times that 1. So it leaves you a 1 in the numerator and what in the denominator? It leaves 1 in the numerator and x times x times x in the denominator. But that means 1 over x to the third. Okay? Now, if 1 over x to the third, if x squared divided by x to the fifth, right here, is the same as 1 over x to the third, right here, and x squared divided by x to the fifth here is equal to x to the negative 3, then ultimately that means that this 1 over x to the third and x to the negative third have to be equal to each other. So that's how we define x to the negative third power, or the negative 3. We say that it's 1 over, it's the reciprocal of x to the third. Pay very close attention. Some people use a little memory tool where they say if your exponent is negative, if you think of an expression as a fraction, so x to the negative third is really x to the negative third over 1, if you want to look at it like that, because any number or any term can be written over 1. But look at it, x to the negative third is in the top part of that fraction. Some people look at it and call this the attic, and call this the basement. I want to use whatever can help you remember this. So if the exponent is negative in the attic, then you move that term, the x and its exponent, to the basement, and it becomes positive. So if I have x to the negative, say, 5, that's the same as 1 over x to the positive 5. Notice when I moved it from the attic to the basement, it became negative. It became positive. And if I move the exponent from the basement to the attic, it changes sign. Watch as we go through some of these examples that we simplify, and it'll become more and more apparent to you what's going on. So let's simplify some expressions by using positive exponents only. Look at what we have here. Negative exponents says if a is a real number other than 0 and n is an integer, then a to the negative n is equal to 1 over a to the positive n. Understand that's the attic and the basement situation there. If it's negative in the attic, if the exponent is negative in the top, then you move it to the bottom and it becomes positive. But notice that the base remains the same. The base doesn't change signs, only the exponent changes sign. So if you want to simplify 5 to the negative 4th power and use only positive exponents, then remember 5 to the negative 4 is in the attic. We want to move it to the basement so it becomes 1 over 5 to the positive 4. Okay? We don't want to leave any negative exponents anywhere in the expression. So let's simplify going down 7x to the negative 4. Now first you have to understand that only the x is to the negative 4th power. That negative 4th power has nothing to do with the 7. So the 7 doesn't have a negative exponent. The 7 has an exponent of 1 that's understood. So the 7 remains in the attic, but the x becomes, the x to the negative 4th becomes x to the positive 4th in the basement. And then it has been simplified. Z to the negative 7 becomes what? 1 over z to the positive 7. We're taking it from the attic to the basement. So this is a negative 2. Notice it's in parentheses. So the negative 2 is the base. Okay? And the base, remember, does not change signs. So what is being raised to the negative 4th power? Negative 2. So it becomes 1 over negative 2 raised to the positive 4th power. Positive 4th power. Okay? Notice I only switched it from the top to the bottom. I didn't change the sign of the base. All I changed was the sign of the exponent. So let's look at these up here. We're simplifying 5 to the negative 1 plus 3 to the negative 1. Well, 5 to the negative 1 is 1 over 5 to the positive 1, which is just 1/5, plus 3 to the negative 1 is 1 over 3. Well, we got to use your calculator or remember how to add fractions. And when you add them together and get the least common denominator and all of that stuff, you get 8 over 15. Okay? Take a minute, go back and process it, because those are numbers raised to a negative power. Negative 4 raised to the second. Notice negative 4 is the base, so that's what has to be brought to the bottom. But the exponent changes from negative to positive. Okay? Two x to the negative 3. What's been being raised to the negative 3 power, negative 3rd power? Only the x. The 2 remains where it is. The x goes to the bottom, and the exponent, I just messed that up. The exponent becomes positive 3. All right. 3y to the negative 4. Here, only the y has a negative 4 as an exponent. So the 3 remains the same. The y goes to the basement, and the 4 becomes a positive 4. Okay? Notice here the helpful hint states that a negative exponent does not affect the sign of its base. I just finished saying that. Doesn't change the sign of the base. Okay? So we have to keep in mind, take a minute and look at this slide and understand what's going on. So when we have a negative exponent in the attic, we move it to the basement and it becomes positive. The exponent becomes positive. When we have a negative exponent in the basement, then we move it to the attic, then the negative exponent becomes positive. So it changes based on its position in the fraction. So let's simplify. 1 over y to the negative 7 becomes, take it to the attic, it becomes, becomes y to the positive 7. Simple as that. 1 over 2 to the negative 5 becomes 2 to the 5th. If you were asked to evaluate it, it would be 2 times 2 times 2 times 2 times 2, which would be, I think, 32. But here you're not asked to evaluate it, you're just asked to simplify it. Now, in this third one, going across, notice that the x has a negative exponent in the attic. The y has a negative exponent in the basement. So we have to change their location. The y needs to come to the attic now, and its exponent becomes positive. The x goes to the basement, and its exponent becomes positive. We can't simplify it any further because they are y's and x's. We can't use any of the rules of exponents that we've learned to simplify that any further. Okay? I'm going to go up here and just place this right here, the 32. All right, so look at the next one. 11 to the negative 2 over 3 to the negative 3. What happens? The 3 comes to the top, and its exponent becomes positive. The 11 goes to the basement, and its exponent becomes positive. And let's go ahead on and just simplify it even more and evaluate it. So we end up with 3 times 3 times 3, which is 27. And 11 times 11, which is 121. So we get 27 over 121 if it's ultimately simplified. Okay? 1 over s to the negative 5th power. So the s has a negative exponent in the basement. We move the exponent and its base up to the attic, s to the positive 5. Next one, what happens? The y has to come to the top with a positive 5 exponent. The x has to go to the bottom with a positive 7. All right. Now, let's simplify some more. Now look at look at the one that we have next, x to the negative 3 and over x to the 2nd power. Well, there's a couple of ways you can do this. Okay? There's a couple of ways you can do it. You can use the quotient rule, and you can say that I have x to the negative x to the negative 3 minus 2, right? Which is equal to x to the negative 5, which then is equal to 1 over x to the 5th. You can do it like that. I want you to write that down, write that process down. I used the quotient rule to do it. But now I'm going to erase it and show you another way of doing it. you can say, well, you know what? I know that x to the second power down here in the bottom is already a positive exponent. So I don't even want to bother with that. I want to leave it where it is. But I can move the x to the negative third power down to join the other x's in the denominator. So I can look at it as 1 over x squared times x to the third. Notice what I did. I just brought my x to the negative 3 down as x to the positive 3. And still we get one over x to the fifth as our simplified expression. All right, next we have 5 over y to the negative 7. Y to the negative 7 is a negative exponent. Bring the y up to the attic. So the 5 remains where it is. The y comes up and the 7 becomes positive. All right. Now the last one here has z over z to the negative 4th power. Notice the negative 4th power can come up to the top, but you already have a z at the top. So we're going to bring times z to the positive 4th to the top. And remember, it's all over 1. But ultimately, what we have here is z to the positive 5th. Using the product rule, z to the 1, z to the first power times z to the 4th power is z to the 5th power. All right. Now, what if we have a base that's a fraction? There's a couple of ways you can do this one. Ultimately, well, let's do it this way. Let's see what this really means. Let's use the power of a quotient rule. If we use the power of a quotient rule, we have to raise the 5 to the negative 2nd power and the 9. So ultimately, if we use the power of a quotient rule, we have 5 to the negative 2 over 9 to the negative 2, which then gives us what? 9 to the positive 2 over 5 to the positive 2. If we move the bases from top to bottom and change the sign of their exponents. So notice what happened. The fraction inside the parentheses, the two terms in those fractions actually flip locations, and the exponents changed from negative to positive. So we can simplify, and if you see a pattern there, you can use that pattern from here on out, but we can simplify this now to 81 over 25. All right, now x over x to the negative 5th becomes x times x to the positive 5th power, which really is going to simplify to x to the 6th. 7 over z to the negative 2. Well, the 7 stays where it is. The z moves to the attic, and the 2 exponent goes from negative to positive. So here we have all of the rules for simplifying exponential expressions. Pause the tape, review these, because you have to know them. Review them, and then move on to the next slide. Okay, now we're going to simplify by writing each expression with positive exponents only. Now, there are a couple of ways you can do either of these. I'm going to show you one way. I don't want to confuse you with different ways, but if you come across another way, which is the same way, it's just that the steps you take might be in a different order. So what I'm going to do is use the power of a product rule. I'm going to raise the 4a to the 4th power. I'm going to take that and raise that to the negative 5th power. Remember, a to the 4 raised to the negative 5th becomes a to the 4 times negative 5, which is negative 20. And b to the negative 3 raised to the negative 5 becomes b to the positive 15. Remember, you multiply the exponents when you're using the power of a product power rule. So we have what now? A to the negative 20, but b to the positive 15. Well, the b to the 15 stays where it is. The a to the negative 20 goes to the basement. And there we have it. Okay? So look at the next one. X squared times x to the 5th cubed. Well, x to the 5th is cubed. So x squared stays the same. X to the 5th becomes x to the 5th cubed becomes x to the 15th. All over x to the 7th. All right? Well, now in the numerator we have x to the 2 plus 15, which is x to the 17th over x to the 7th. And then using the quotient rule, now we have x to the 17 minus 7, x to the 10th. Okay? Here we have a quotient raised to a negative power. So we raise everything inside of there to the negative 2 power. So 5 gets raised to the negative 2. P to the 8th gets raised to the negative 2. It becomes negative 16. The Q gets raised to the negative 2. Okay? So what happens? Everything has a negative exponent. The 5 has a negative exponent, the P has a negative exponent, and the Q has a negative exponent. So all of those things have to change their location. If they're in the attic, move them to the basement. If they're in the basement, move up to the attic and change the sign of the exponent. So Q to the negative 2 moves to the attic and it becomes Q to the positive. 5 to the negative 2 becomes 5 to the positive 2 in the bottom. P to the negative 16 becomes P to the positive 16. And in the end, we get Q squared over 5 squared, which is 25, times P to the 16th. Okay? There are people who are going to want to simplify using the quotient rule. The next problem, you can use the quotient rule to simplify this. You can. But I personally just like to take all my negatives and move them so that they become positive and then simplify. So for instance, I have a 6 to the negative 2 I want to bring to the bottom and make it 6 squared. And a 6 to the negative 3 becomes 6 to the 3rd at the top. Then I have an x cubed that's positive in the denominator. And I have an x to the negative 4th in the numerator that I want to bring to the bottom as a positive 4, x to the positive 4. Okay, so my x to the 4th has come, x to the negative 4th has come to the bottom. Now I'm going to flip my y to the negative 9 and y to the negative 7. So I'm going to put y to the negative 9 at the top as a positive 9. And y to the negative 7 at the bottom as a positive 7. Take a minute and digest that. Then we can go and simplify. All right, so 6 to the 3rd power divided by 6 to the 2nd power. If you do the arithmetic and know your rules for exponents, it's just 6. Okay, y to the 9th divided by y to the 7th leaves us a y squared at the top. And I'm going to move it closer because we're not going to have any x's in the top. Y squared at the top. And at the bottom, we have x to the third times x to the fourth, which is x to the seventh. Take a minute, process it, find another problem similar to that, and work it. Let's do one last one, okay? Let's raise this whole expression to the third power, which means everything in the numerator and everything in the denominator has to be raised to the third. So, we have -3 to the third. We have x to the fourth to the third, which really is x to the fourth times 3, which is x to the 12th. And then we have y to the third, all over x to the second raised to the third, which gives you x to the sixth, and y to the -2 raised to the third, which is y to the -6. Okay? Alright, so -3 to the third. Well, let me see. 3 to the third is 27. So -3 to the third is -3 times -3 times -3, which is -27. Okay, notice it's to the third power. Okay, so it's -27 x to the 12th over x to the 6th. Notice there's an x to the 6th right here and x to the 12th here. We can use the quotient rule there, and they end up with x to the 6th in the top. Okay, now the y to the -6 here can move to the top as well. Okay, the y to the third up there is already positive exponent, so we leave that one alone. Move the y to the 6th up to the top, and that gives us y to the 6th times y to the third, which is y to the 6th plus 3, which is y to the 9th. So we have simplified it to -27 x to the 6th, y to the 9th. Okay? Writing numbers in scientific notation. Scientific notation makes the use of exponents and powers of 10. When we raise powers, when we raise 10 to some powers, we get numbers like 10, 100, 1,000, 10,000, 1 million, whatever. And you can raise it to negative powers of 10, which gives you the decimal versions like 1/10, 1/100th, 1,000th, all of those decimals that end with TH. Well, writing numbers in scientific notation allows you to write really, really, really large numbers and really, really small numbers in a notation that's easier to read. Now, if you looked at the mass of the Earth, I can't even read this number. I don't know what this number is, but that's how many kilograms they're estimating that the Earth weighs. Okay, the mass of the Earth. But that thing has 1, 2, 3, 6, 9, 12, 15, 18, 21 zeros. But if I were to move the decimal from where it is, now where's the decimal? I can't get my pen to work. The decimal, because this is a whole number, the decimal is back here where I'm putting this pink spot. If we move the decimal 3 places, 6, 9, 12, 15, 18, 21, 24 places, and drop it off between the 5 and the 9, if I drop that decimal off there, that 5.972 is a number between 1 and 10. Notice what I'm saying. 5.972 is between 1 and 10. Okay? The way you write scientific notation is by having a number between 1 and 10 times some power of 10. So another way to write this big long number would be 5.972 times 10 to the 24th power. Okay, because we moved the decimal 24 places to the left to make that number 5.972, make it a number between 1 and 10. Okay, you'll get a little practice. Just roll with me here. Now, the mass of an electron. Remember, an electron is a part of an atom. The atoms are very small, so the things they're made of have to be very, very small. Notice the decimal place in the atom, the mass of an electron. The decimal is here, and you've got a bunch of zeros after it before you ever get to a non-zero number, which is 9 right here. Well, this is hard enough to read, but how many places would we have to move? Pretend this decimal right here is not there. Pretend that was not there, because you can't have two decimals. I made a mistake. I had the decimal here and a decimal here. Pretend this one is not there. But pretend that we're moving it from here, 3, 6, 9, 12, 15, 18, 21, 24, 27, 30. We moved it 31 places to make it a number between 1 and 10. So we had to move the decimal 31 times to make this non-zero part, the 9, the 1, 0, 9, 3, 8, 2, to make that a number between 1 and 10. We moved our decimal 31 times. So ultimately what we got was 9.10938291, if you want, times 10 to the negative 31. And 10 to the negative 31, see, when you have a negative exponent, you know you're dealing with a really, really small number. So this is a very, very, very small number. Whereas the mass of the Earth up here is a very, very big number. So its exponent is a positive. This one has a negative exponent. Okay, so here is a rule for writing a number in scientific notation. A positive number is written in scientific notation if it is written as the product of a number A, where A is between 1 and 10, and an integer power of 10. So if A has to be between 1 and 10, and the exponent on the 10 has to be an integer, meaning it can be positive or negative, it just can't be a fraction. So to write a number in scientific notation, step 1, move the decimal point in the original number to the left or right so that the new number has a value between 1 and 10. Number 2, count the number of decimal places the decimal point is moved in step 1. If the original number is 10 or greater, the original number that you were given is 10 or greater, the count is positive. If the original number is less than 1, the count is negative. What is that saying? And well, and it says multiply the new number in step 1 by 10 raised to an exponent equal to the count found in step 2. It's a whole lot of words. Watch what I do here. We have a number, 0.000007. I want to write it in scientific notation. I'm going to count the number of decimal places it takes me. 1, 2, 3, 4, 5, 6 to make that a whole number, to make it a number between 1 and 10. If I move my decimal here, that's 7. 7 is between 1 and 10. But how many places did I move it? 1, 2, 3, 4, 5, 6. So that becomes 7 times 10 to the negative 6. Negative 6 because that number, this original number, is a small number. It's less than 1. So it has to be a negative exponent. This number here is a big number, so when we move our decimal, it's going to be a positive exponent. So we know we're going to move it 1, 2, 3, 4, 5, 6, 7 places to make it a number between 1 and 10. So that gives us 2.07 times 10 to the what? We counted 3, 6, 7 places. 10 to the 7th. 0.0043, we move the decimal from where it is 3 places to make that a 4.3. 4.3 is between 1 and 10. That's why we stopped there. So we get 4.3 times 10 to the what? Is it going to be a positive exponent or negative? Excuse me, negative exponent, because the original number is less than 1. And we moved it 1, 2, 3 places. So it becomes 10 to the negative 3. 4.3 times 10 to the negative 3. $812 million. That's what this is. It's a pretty big number. So I need to write it in scientific notation. Well, I know my answer is going to have a positive exponent. 3, 6, 7, 8 places I had to move the decimal. So I'm going to park it right between the 8 and the 1. So 8.12 times 10 to the, what did I say? 3, 6, 10 to the 8th. This is 9,060,000,000. Well, let's move our decimal place and see. 1, 2, 3, 4, 5, 6, 7, 8, 9 places. So we have 9.06 times 10 to the positive 9 or negative 9? Positive 9. Okay? Now we want to go from scientific notation to standard form. Now here you're going to be moving your decimals in order to write the number in standard form. So basically we're going to be moving our decimals in the opposite direction from what we were doing before. But watch what happens. The first one here, we have 3.67 times 10 to the negative 4. Well, 10 to the negative 4 means this is a small number, which means I'm going to have to make it a small looking number. It's going to have a bunch of decimal places. So we're going to move the decimal from where it is. 1, 2, basically I'm moving it to the left. Okay, I don't have enough room here to do it, but I'm moving the number, the decimal. I'm gonna go ahead on and write it again. So if I have 3.67, I need to move the decimal from where it is 4 places, because that's what this says, to the left. 1, 2, 3, 4. I'm going to drop a decimal there, and everywhere that I have a little bump, I'm going to put a 0 in there. So I need to rewrite this as 0.0000367. So I've moved the decimal to the left 4 places, and I've dropped the decimal there, and I've written this in standard form, or standard notation. Now 8.954 times 10 to the 6th, that's a big number because the exponent is positive, so I need to move my decimal now to the right. So I take my 8.954 and I move my decimal 6 places to the right from where it is. 1, 2, 3, 4, 5, 6. And then I insert the zeros to make up for those bumps or humps. So that leaves me with 8,954,000, which is 8,954,000. Okay, now 2.09 times 10 to the negative 5th. Well, we have 009. And this one's to the negative power, so we need to move it to the left. Move the decimal to the left. 1, 2, 3, 4, 5. Drop off that decimal and insert some zeros. Here, 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 and here. So ultimately we have 0.0002009. Okay? Last one here. This one is a big number because the exponent is positive. So we have 4.054, and we take the decimal and move it to the right 3 places. 1, 2, 3, which gives us 4,054. Okay? So that's changing from scientific notation to standard form. Now here, when we multiply numbers and divide them in scientific notation, what you have to remember is scientific notation is a multiplication problem. So we have 5 times 10 to the negative 4, and that is times 8 times 10 to the 6th power. So you can really rearrange these terms inside of here if you want to. You can just say, you know what, 5 times 8, I can separate those because it's all multiplication, times 10 to the negative 4 times 10 to the 6th. And then you can use your power rules and all of those rules if you so choose. So we have 5 times 8, which is 40, and then 10 to the negative 4. We're adding negative 4 and 6 gives us 10 to the 2nd power. But notice that 40 times 10 to the 2nd power is not in scientific notation. Why? Because 40 is not between 1 and 10. So we have to account for that. We have to move the decimal from where it is back over 1 place to the left to make it a number between 1 and 10. Make that a 4. So we get 4 now times 10 to the 3rd power, and that is in scientific notation. Now look at those two numbers. Look at these two here. If you have 40 times 10 to the 2nd power, what was 10 to the 2nd power? It's 100, right? Well, 40 times 100 is what? 40 times 100 is 4,000, right? 40 times 100 is 4,000. But 4 times 10 to the 3rd here is 4 times 1,000, because 10 to the 3rd is 1,000. 4 times 10 to the third is 1,000. And 40 times 10 to the second is, 4,000. 40 times 10 to the second is 4,000. 4 times 10 to the third is 4,000. So they're equal to each other. It's just that the last one I wrote is in standard scientific notation. Scientific notation. So be careful that when you are working these problems that you're actually putting it in scientific notation. Okay? It has to be a number between 1 and 10. Okay? Same thing with the division. We can divide 64 by 32, and that gives us 2, and times 10 to the what? 10 to the what? Well, you can bring that 10 to the negative 7 up to the top, and it becomes 10 to the positive 7, and combine it with the 10 to the third, and it becomes 10 to the 10th. And this one is already in scientific notation because the 2 is between 1 and 10. 9 times 10 to the 7th times 4 times 10 to the 9th becomes 9 times 4 times 10 to the 7 plus negative 9. So that becomes a negative 2. All right? Which is ultimately going to give us 9 times 4 is what? 36 times 10 to the negative 2. But 36 is not in scientific notation. 36 is not between 1 and 10. So we need to move the decimal one place to the left, make it 3.6 times 10 to the what? Well, what did we do when we moved it to the left the last time? We increased our exponent by 1. Notice up here, we increased the 2 to a 3. We increased it by 1. Well, we need to increase this negative 2 by 1. But be careful when you increase a negative 2 by 1. Remember, you add 1 to it, it becomes to the negative 1. Remember, when you add a positive 1, when you increase this number, negative 2, by 1, when you add 1 to it, you get a negative 1. So ultimately, this is our answer, 3.6 times 10 to the negative 1. Here we're going to divide. 8 divided by 2 is 4. 10 to the 4th divided by 10 to the negative 3rd becomes 10 to the positive 7. All I do is bring the negative 10 to the negative 3 up to the top. And we get 10 to the negative 7. And you've just performed a couple of operations with scientific notation. We're not going to do too much with scientific notation, but you have to at least know how to work with it, have to understand where it's coming from. We'll have 1 or 2 problems on our test, and then actually we won't see it anymore until our final. So good luck. See you soon.